Okay, so to understand Bohr's model of the atom fully, we have to consider waves. And from the, let's just do a couple of definitions here of the properties of waves. Now, there's a line that kind of goes through the middle of the wave, which is called the normal. It's not real, but it's how we measure the height of the wave, also called the amplitude of the wave. Normal would be where, if you remember the spring demonstration, is where the spring rests when there's no wave in it. Okay, so amplitude represents the height of the wave. And for light waves, that really just determines the intensity of, or the brightness of the light. If it's a high amplitude wave, that's indicating a very intense light. Now for sound, you guys have probably heard of an amplifier before. Do any of you play like electric guitar? No one plays the electric guitar? I can't hear you. You guys, what do we do with our electric guitars? We plug them into a what? An amp, right? What is amp short for? An amplifier. So you've got your electric guitar when it's not plugged in. You can pluck the strings. You barely hear it, right? So that wave is moving along the string at a certain frequency. We plug it into the amp, and what does the amp do? It makes the wave a lot taller, which means it's going to be louder as it travels through the air, compressing the air and expanding the air. When it hits your eardrum, you can hear it. And it does not change the frequency of the wave, so it doesn't change the speed of the wave at all. We're not going to look too much at amplitude, but I just thought I would mention that because it's something that you're familiar with. Frequency, the variable that we use to indicate frequency is, I use a V because I can't really find the Greek letter nu, which is what it is. But we can kind of think of it as a velocity as well. Physicists would get upset about that, but so Eric, like, I'm going to use velocity. I'm going to use that for frequency. Don't be offended. Frequency is the speed of the wave, and that's measured in waves that pass a particular point per second. Let's be consistent and just use S, standing for seconds. Now, typically, we don't usually use the unit wave. So for frequency, we would say the unit is the reciprocal of a second. And another way of writing that, so these all mean the same thing. Wavelength is indicated with this Greek letter lambda. Kind of looks like an upside down Y. And of course, it is a length, right? So what unit do you think that length is measured in? Are you saying something and I just can't hear you? Length, the SI unit for length is? What is it? Meter. Right. Now, typically these are not lengths that we can see really well, so we would measure it in a meter. The one on the spring we could measure in a meter. However, much more commonly when we're dealing with light, we're going to measure that in nanometers. Do you guys remember that nano is 10 to the negative 9 meters? Now tomorrow you're going to use a tool called a spectroscope, and that is going to measure the length in angstroms. The symbol that we use for angstrom is this A with a 0 over top of it. And 1 angstrom is 10 to the negative 10 meters. Your spectroscope actually measures in kilo angstroms. We'll look at that more closely tomorrow. So you can see that the wavelength is measured typically from crest to crest or trough to trough. It does not have to be measured there. It can be measured at any similar point along the wave. It's just that crests and troughs are easy to see. So we tend to measure it there. So we have wavelength, the amplitude of the wave, which we're not going to look too much about, and then the frequency. Now from the spring demonstration, when wavelength goes up, or let's go the other way. When wavelength decreases, what happens to the frequency or the speed of the wave? So smaller wavelengths mean what about the wave? It's doing what? It's what? Going faster. So as one increases, the other decreases, right? That's an inverse relationship. So what we're showing here is that wavelength and frequency are inversely proportional, and they're inversely proportional according to the speed of light. So here's a mathematical expression that you'll be using this unit. Another way to write that is that the speed of light is equal to wavelength times frequency. But I like this second way because you can see the inverse relationship between wavelength and frequency. And then the other relationship that you're going to need to know is one that was developed by someone named Robert Planck. Robert? Am I thinking of I think I'm thinking of a singer. Anyway, what happens to the frequency of the wave as you increase energy? You saw that when I put in more energy, what happened to the frequency? Did it go up or down? It went up, right? So that's a direct relationship. And then there's also a constant in there that is going to kind of manage, I guess, that frequency. If you were to plot energy versus frequency, this constant here is the slope of the line. So c represents the speed of light. And that's a constant 3.0 times 10 to the 8th meters per second. I do not expect you to memorize that number. Some of you will just from using it. That's the kind of brain you have, but I will provide you that number. And then h is something called Planck's constant. We'll look at that on another slide. Yes, sir. 3 times 10 to the 8th. Got it? Oh, whoops. Forgot about that. Sorry. Yeah, so Planck is the person who was studying the energy of the wave. And this is interesting. He was studying hot glowing solids. Like, do any of you have an electric stove at home with the coils? No? You turn on your electric stove, what color does it glow? Orange. That's exactly what he was studying. He would take a solid and heat it up and go, that is orange. And then he would heat it up and it'd be like, that is blue. So he was studying these different solids that he heated. And basically he said that the more energy you put in, the higher the frequency of color that comes off. What he could see. Remember that our eyes only see a really small amount of waves. And this was his relationship. Energy and frequency are directly proportional, and that h is Planck's constant. 6.626 times 10 to the negative 34 joule seconds. That is not a joule per second, it's a joule times a second. So these are the observations that led to Bohr's model of the atom. And Bohr was studying glowing gases, whereas Planck was studying glowing solids. So Bohr was basically studying a cathode ray tube again. But this time, he was holding up a prism to the light that was coming off of the cathode ray tube. And when he held a prism up, this is what he saw. This is called a bright line spectrum. If you hold a prism up to white light, you'll see a continuous spectrum. I think I stole this from a British site. That's why it says But this is a continuous spectrum. Okay. And then we can ignore an absorption spectrum. That's for dyes. But emission spectra, instead of providing all of the different colors that are in the spectrum, you only see certain wavelengths of color. And that's what Bohr was trying to explain with his model of the atom. He was like, how come all of the different energies associated with the wavelengths are not present? How come just these are present in the atom? And his model was a mathematical model. And it worked really well for the element hydrogen. Like, he could predict what he would see when he put a certain amount of energy into hydrogen. But then when he got to more electrons, like hydrogen only has one electron, and his mathematics were perfect. But then, like, he started using helium and other elements, and it all fell apart. However, he gave us an idea of what was happening with the electrons. The problem is, like, at this time when we were studying motion, everything was following Newton's laws of motion. Force is equal to mass times acceleration, and Newton's other laws of motion. The problem is when you're dealing with something that's really, really small and it's moving really, really fast, those Newton's laws of motion kind of fall apart. And that brings up a study called quantum physics. And we didn't have a good knowledge of quantum physics for a really long time, probably not starting until the 1930s did we start looking at how things are different if they're really small and moving really, really fast. And that brings about Einstein and his theories. So Bohr was studying hot glowing gases, and basically he came up with this planetary model. And this is what he said. For hydrogen, there are only 4 energy levels. Now, you see how I put visible in there? That's because that's all we could see. That does not mean that there weren't other energies coming off of that spectrum. And when, by looking at that, he looked at that bright line and said, oh, there's 4 energy levels. Electrons in an atom are quantized, meaning they only have a certain energy. I think your book uses a stair-step analogy where, you know, if you're going up or down the stairs, there's nothing in the middle of the stairs. You can't have a half step, right? You either take the step of the stair or you don't. And Bohr said that the lines from the spectrum are formed when an electron is moving between 2 of these energy levels. So what's happening is the electron is gaining energy from the energy source. It's jumping to a higher energy level, which is called the excited state. And when it returns back to its normal position, which is what we call ground state, it gives off this light. And we can see that if we hold it up to a prism. A prism's purpose is to bend the light. And his model was called the planetary model, because what he basically said was the electrons are moving around the nucleus in a defined path, in an orbit. And we can make it move by adding energy to it, but then it goes directly back to its other path. He was close, but he didn't get it. Whoops. That's where we want to stop. Okay, so those are the four big players of atomic theory: Dalton, Thomson, Rutherford, and Bohr. In tomorrow's lab, you're going to be looking at the bright line spectrums that Bohr was looking at and doing some calculations with those regarding energy, wavelength, and frequency.